You hit save probably a dozen times a day. It feels instant, just a simple click. But behind that click, there's this hidden world, a whole journey your data takes. So today, we're going to pull back the curtain and explore the secret life of a saved file. And we'll start with a question you've definitely had if you're a gamer. Seriously, think about it. When you save your game, the computer isn't just taking a quick picture. It has to remember everything. Your character's health, every single item in your inventory, your exact coordinates in some massive sprawling world. All of that incredibly complex information has to be packed up, stored away, and then perfectly reloaded the next time you play. How in the world does it do that? Well, that's the big mystery we're solving today.
Okay, so to figure this all out, we've got to start with the absolute fundamentals. First things first, what even is a computer file, really? And are there some universal rules for how we interact with them?
At the end of the day, a computer file is just a container. It's a box for information. It doesn't matter if it's a photo, a text message, a video, or even the program you're running. It's all just data that's been recorded and given a name on a storage device, like your hard drive.
And believe it or not, every single interaction with any file, no matter how complicated it seems, boils down to these three simple steps. First, a program asks the operating system to open the file. It's basically asking for permission to get in. Then it's either going to read data from the file into the computer's memory or write new data from memory into the file. And then, and this part is super important, it closes the file, which tells the operating system, hey, I'm done here, you can let go now. Okay, now here's where things start to get really cool. Moving that data back and forth isn't just a big, clunky data dump. It happens through this really elegant concept called a stream. A stream is, well, it's pretty much exactly what it sounds like. Imagine a continuous flow, a river of data. Instead of trying to grab all the information at once, the computer treats it as a sequence of tiny pieces, flowing from a source, like a file on your hard drive or your keyboard, to a destination, like your program or your computer screen. It's a really powerful way to think about data.
So why is this idea so powerful? Well, think about it. Your application needs to talk to all kinds of different things. Your keyboard, your monitor, your printer, your hard drive. Instead of the programmer having to write unique custom code for every single piece of hardware, they just write to one generic thing, the stream. The operating system then handles all the nitty-gritty details of talking to the specific device. It's brilliant.
And for the program itself? Oh, this makes life so much easier. It doesn't have to care if the data is a picture, a song, or a text file. To the stream, it's all just a simple sequence of numbers, or what we call bytes. You have an input stream bringing those bytes in, and an output stream sending those bytes out. It's this beautiful, simple, and incredibly flexible system.
So we've got files, and we've got streams to move the data around. Problem solved, right? Sounds like we're all set. Well, not so fast. This beautifully simple system runs headfirst into two huge problems when you try to use it for real-world stuff.
So let's meet our two big troublemakers. First, complex data. A stream is just a flow of numbers. It has no idea what a high score or player health even means. How do you save that kind of structured information? And second, performance. I mean, if you have a massive video file, reading it one single byte at a time is unbelievably slow. It's like trying to fill a swimming pool with an eyedropper.
And that eyedropper method in actual code looks a little something like this. The real problem is that loop. It tells the computer, okay, go all the way to the hard drive, grab one tiny byte, bring it back, do something with it, and now go all the way back to the hard drive to get the very next one. Doing that millions or billions of times creates a traffic jam of epic proportions. Okay, so let's tackle problem number one. How do we save those complex data structures? The solution is a process with a really cool name, serialization.
I absolutely love this analogy. Think about it. Serialization takes a complex object that's living in your program's memory, like all the info about your game character, and it carefully translates it piece by piece into a simple format that can be written out as a stream of bytes. It's exactly like disassembling your IKEA furniture, packing it flat in the box so it's easy to ship or store, and later you can do the reverse, deserialization, to build it right back up.
And, developers have a whole toolkit for how to pack that data. You've got binary formats, which are super small and blazing fast for the computer to read, and then you have formats like JSON and YAML, which are actually readable by humans. These are perfect for things like configuration files or for different computer systems that need to talk to each other.
All right, one problem down, one to go. Now for our second villain, that terrible performance. How do we solve the problem of reading a huge file one
tiny byte at a time. Well, the solution is all about working smarter, not harder.
So the key to understanding this is right here in this quote. Every single time your program wants to read something from the disk, it has to make a special request to the operating system. And that request is a heavy operation. It's just slow. It takes a lot of time and resources. So doing that millions of times is what's killing our performance.
The smart solution is called buffering. So instead of using a simple, basic file reader, a programmer will use a smarter tool, like this buffered reader. See how it wraps around the basic reader? It acts like a clever middleman. Instead of making thousands of tiny trips to the disk, it makes one big trip, grabs a huge chunk of the file, called a buffer, and stores it in the super-fast computer memory. Then your program just reads from that memory buffer, which is thousands of times faster than going to the disk every time.
And hey, don't just take my word for it. These technical choices have a huge, real-world impact. Just look at this data. This compares how long it takes to load data using two different formats, JSON and YAML. Wow, JSON is way faster. Now, these are fractions of a second, but when your app has to do this over and over, those tiny moments add up like crazy and make a huge difference in how fast an application feels.
So, from that one simple click, your complex data gets serialized, packed flat for its journey. Then it's sent through a buffered stream, moving in these big, efficient chunks, before finally getting written as a long sequence of bytes onto your desk. It's this whole hidden, elegant dance happening in milliseconds. Kind of makes you look at that save button a little differently, doesn't it?